Welcome back to this lecture on architecture and programming models for GPUs and coprocessors. In the meantime, we're about halfway in. We're still talking about rendering algorithms, and we're in the middle of discussing the ray tracing algorithm. Last time, in particular, we learned about weighted ray tracing, and today we are going to discuss how to increase realism even more. And we will also learn that an increase in realism usually comes at an increase in computational time. And we're also going to learn about strategies, how to mitigate this increase in computation time, and about acceleration techniques that can be applied to ray tracing in general. So the setting that we discussed last time was one where we had our ray tracing algorithm, and the ray tracing algorithm was concerned with what essentially were lots of delta distributions. Like this actually starts at the viewing position, where we assume that the viewing position is just infinitesimal, and the camera model is basically a pinhole camera. And therefore the lens doesn't have an area, and therefore we can just shoot single rays from the camera. And then when we shoot our rays from the camera, they potentially hit something like a surface that is reflective. And then we shoot more rays, like rays that are reflected into the perfect specular reflection direction. And then they're potentially reflected again, or they are refracted, and so on. And whenever we hit a surface, we assume that the surface properties follow a so-called delta distribution. And the same is true for light sources. That is, whenever we evaluate shadows, whenever we evaluate visibility, we assume that light sources are infinitesimal, and that we can just shoot a single ray towards the light sources. And of course, this results in images that depict those phenomena, but where the realism is relatively low, because hard shadows are pretty seldom in reality. Like they actually only occur with light sources that are very far away, like the sun, for instance. And perfect mirrors are also an idealized model that doesn't happen in reality. And therefore, in order to introduce more realism into our models, we have to lift this restriction that surfaces and phenomena in general behave like delta distributions. Like for instance, if we want to allow for effects like defocal blur and objects being out of focus, depending on where we're currently looking, we for instance have to give the lens a finite area. Like we would introduce a lens that has a certain area to it, and then we would sample that lens, and like whenever we sample, like the phenomena here follow the very same laws and are subject to the same restrictions that we discussed when we talked about sampling theory. Like if we were to sample that lens with a uniform pattern, then this would manifest as objectionable artifacts. And at the same time, if we undersample the lens, then this will result in aliasing. And that means as soon as we introduce phenomena that don't follow delta distributions, we have to shoot significantly more rays to sufficiently sample the phenomena. So, and this can be done for the lenses, but this can actually be done for all kinds of phenomena. Like for instance, when we hit a reflective surface, then in the delta distribution and the Turner-Whitted model, we would just shoot a single ray in the single preferential direction. That is, we would sample the delta distribution, which of course is trivial. And in the case where we allow for rough surfaces, we allow for a reflection in a cone around that preferential direction, and so we have to sample that cone. And when we do so, we actually have to shoot many more rays in order to not undersample the phenomenon. And like the same thing can be done, for instance, for light sources. Like when we want to allow for soft shadows with soft shadow penumbra, then we lift the restriction that light sources are points, and instead give them an area, and then we have to sample that area. And like to give you an idea, usually when one introduces direct lighting with a area light sources, a typical sampling rate for that is somewhere between 16 and 64 rays. So the additional amount of rays that we have to shoot to faithfully depict those phenomena without artifacts is actually huge. So when we can sample all sorts of effects, given that we devote more rays to the problem, like for instance, we can also model materials that are dielectrics and that still have surface roughness, like a rough glass, for instance, behaves that way. So whenever we increase realism, we do this at the cost of having to add many more rays. Like when we consider the ray tree that we discussed in the context of the widget ray tracing algorithm, we had this binary tree, like with a branching factor of 2. And whenever we hit a dielectric, we would shoot a reflected ray and a refracted ray. And whenever we hit a perfect mirror, we would just shoot a reflected ray. So that would give us, for a single primary ray, that would give us a ray tree that would look something like this. Like we're maybe assuming that we're breaking after a certain number of bounces. So the ray tree would look something like this. And as soon as we introduce like phenomena like rough surfaces, for instance, this starts to explode, right? Because we have at those branching points, we have to increase the arity of the tree. So what before was a binary tree is now an n-ary tree. And the problem is that the construction of the tree is of course recursive. That is, whenever we hit something, we have to do the same branching at those hit points too, right? And I mean, you can imagine that this will explode at some point, and we will just end up with an exponential growth of the size of this tree. And this is of course not feasible. Even for small scenes, this is not feasible. And even if we were now to allow for lenses that have an area, for instance, we would just have to duplicate this tree like a couple of times just to reflect the fact that there is more than one primary ray per lens sample. So this would explode, would result in an exponential size of the tree pretty soon. And this is of course not viable, and therefore we have to talk about strategies to keep the size, to keep the number of rays relatively low. So this is one objective that we have, that we sample all those phenomena, and that we sample them in a way that we can achieve high realism, and at the same time minimize the number of rays that is necessary for that. And then at the same time, there's also this issue, like in the naive formulation of the algorithm that we assumed so far, the computation time is just so high because we have to, whenever we spawn a ray and shoot a ray into the scene, for instance, because it was reflected, we have to test that ray against the whole scene geometry. Like when we're evaluating closest hit, we have to touch each and every triangle and test if the ray hits the triangle in order to find the closest hit. And this is of course also a source of inefficiency that we should deal with. And therefore today's session is on the one hand going to be about how to increase realism, and we'll see some very nice images, and at the same time we really have to talk about how to increase efficiency and how to make this procedure of tracing rays through the scene more efficient, and how to minimize the number of rays that we use in order to do so. And this will be the topic of today's session. And before we start talking about efficiency, let's just have a look at those various phenomena and how to integrate them into our ray tracer. And let's also have a look at what those images would look like when we use those newly added techniques. Like, let's for instance talk about soft shadows and area light sources. Like, as soon as we're interested in soft shadows with shadow penumbra, then we have to give our light sources an area. And that means whenever we hit something, when we're at a hit point, instead of shooting a single ray toward the light source, we will shoot a bunch of rays toward the light source, and then compute an average contribution. Like, our visibility term will now no longer be a binary term like 0 or 1. There will be a binary term for each of those samples, and then we will average those binary terms. And this will give us a percentage that tells us how much of the light is actually occluded and how much of the light comes through. So the principle is relatively simple. What we can see is that area lights are actually very prone to uniform sampling patterns. So we usually have some type of jittered or randomized sampling pattern on the area of the light source. And like when I replace the area lights, the light source here at the ceiling of the Cornell box with an area light source, then things actually become much nicer. Like we can already see how those soft shadows increase the image fidelity quite a lot, right? Like we now have an area light source, and whenever I'm at a certain point here in space, at a hit point, instead of shooting only one ray towards the light source, as I'm doing here on the left side in the image on the left, you can see here in the image on the right, you can see how I use more rays and how I use area light sources in order to compute soft shadows, and also you can also see how that increases image fidelity, right? And like the same is true when we want to incorporate rough surfaces. Like rough surfaces will follow a construction law where there is a non-zero probability of light being reflected not only in the preferential direction, like in the mirror direction, but in a cone around that mirror direction. Like where we get that cone from, like with very simple models, they're just the specular cones, like we computed them before. And there are actually more complicated models that account for anisotropy, like metals, for example, behave like that. So it's not so important where we obtain the cone's preferential direction from. But what's important here is that we have to sample that whole cone, right? And we again use many more rays. So in here you can see what that would actually look like. Like what I'm doing here is I'm varying the roughness, the surface roughness of the material that is assigned to those boxes here in the background, right? And you can see that those green boxes and the dragon model are reflected into the surface. And you can see that the roughness is relatively high here in the image on the left. Like you can still see the green and the orange color of the dragon and of the boxes being reflected onto the material. But you can see that the light contribution is kind of scattered. And with varying roughness, like when I'm increasing the shininess, the material behaves more and more like a mirror, because that cone, the radius of that cone actually becomes more narrow. And therefore we are sampling closer to the preferential direction that the light would be reflected into if we had perfect specular reflection. And that is by decreasing roughness and by increasing shininess, we're gradually approaching a model that is similar to the perfect specular model. So, and then in the end, like the ultimate phenomenon, so to say, is so-called full global illumination. And what distinguishes full global illumination from like local illumination or ray traced illumination with rough surfaces like we saw before and with soft shadows is the fact that we are also now incorporating diffuse reflection into our renders. Like, what that means is, like before, we were only considering reflections for surfaces that had some type of preferential direction, like where we could find a cone of preferential directions and then we would sample that. And as a matter of fact, like surfaces that are just diffuse, like the Lambert surfaces, for instance, that we discussed earlier, they also exhibit reflection, of course, but the reflection has like an equal probability over the whole hemisphere. Of course, that makes sampling those distributions much more compute intensive, because the wider the cone gets, and this is basically what's happening, like conceptually, a diffuse model can be thought of as a material model that is fully rough, where like the cone of preferential directions extends into all directions and like extends towards the whole hemisphere, and therefore we have to sample the whole hemisphere. And you can imagine that if we have equal probability of light being reflected on the whole hemisphere, that we have to devote many more rays just because of the surface area of the hemisphere usually being higher than the surface area that is prescribed by the radius of the cone of preferential directions. So and this is basically it. Like when we're saying we're computing global illumination, that usually means that we're also taking diffuse interreflection into account. And where you can see this is here on those images. You can see that this manifests as so-called color bleeding, where you basically have diffuse reflection of that green and red color from the walls onto the gray or beige color of the floor and of the ceiling. Like for instance, here in this corner, you can very nicely see the effect of color bleeding. And this is an effect that you can only simulate if you take a global illumination and if you take diffuse interreflections into account. And this is so compute intensive that it's actually completely infeasible to do with a wide ray tree as we saw it in the widget model. And for those reasons, people, when they compute global illumination, they finally use an algorithm that is called path tracing. And the path tracing algorithm can be thought of as one way to mitigate those exploding ray trees that we talked about earlier. And therefore, we should have a quick look into how a path tracer actually works. A path tracer being one constituent of the family of ray tracing algorithms that we're currently discussing. And we're now going to very briefly discuss the path tracing algorithm. Like, what's important to us is to gain an intuition, understand the basic principle, but we're not going to analyze the algorithm as rigorously as we did with the other ray tracing algorithms. And in the path tracing setting, what we're presented with is the same scene that we had before. And the scene is now comprised of entities that don't follow delta distributions. Like, it is possible to support delta distributions in a path tracing pipeline too, but it's not what people typically do. We instead have finite lenses, we have area light sources, we have BRDFs that are in general not delta distributions. And what we now basically do is we perform a Monte Carlo simulation in order to integrate radians. So, and for that, for each pixel sample that we are taking, we're initializing a random number generator that will provide us with uniformly distributed random numbers on the interval from 0 to 1. And we will use this uniform random number generator to perform basically what is a random walk through the scene. And that random walk starts at the viewing position, and then we just sample with the random number generator a position on the lens and trace a ray through the lens according to that position. And then we will follow that ray and intersect the ray with the scene geometry. And then we will, like with the widget ray tracing algorithm, we would potentially generate a bunch of rays. Like we would potentially generate a refracted ray and a reflected ray. And if we have a glossy surface, we would maybe just shoot 5 or 6 rays that are distributed with respect to the cone of the reflection direction. And we don't do that, but instead, we really only pick a single direction. And a single direction that we will use to continue this path. So for that, let us just assume that we have a diffuse material here, and we're in a ray tracer, like in the setting that we were in before, we would just have to sample that whole hemisphere, right? And we're not doing that, but instead we're just picking a single sample. We're picking that single sample, and that single sample tells us how to extend our path, and then we just follow that single ray. So, and in this case, we would find that the ray that we extend doesn't hit anything, so it misses, and therefore the radiance contribution of this whole path is 0. Like the radiance that is returned would evaluate to the RGB color black. And then we trace more such rays, and whenever we're at a hit point, we use our random number generator to generate samples on hemispheres or inside of cones. And only if we eventually hit a light source, that path contributes. And when that path contributes, then we take the accumulated radiance and have that accumulated radiance contribute to the pixel color. And this is an algorithm where we will compute convergence. That is, we repeat this process over and over again. Like we will sample our lens, and then we'll sample our image plane, and then we'll on average have several samples that we take per pixel, and those several samples will be averaged, and then eventually make up the final pixel color, like after some time after the algorithm has converged. And the convergence rate is actually due to the efficiency of the sampling methods that we use. Like, for instance, there are certain methods that allow us to importance sample the various functions. Like, for instance, if there is only a cone of preferential directions, then we know that there's zero probability for all reflected directions outside of that cone. And all directions outside of that cone will just contribute black because they have zero probability. And therefore we import and sample only the cone. And so there are like a bunch of techniques that we can use to increase the efficiency of that procedure. But the gist of this procedure is that we have like a bunch of paths, and many of those paths potentially will not contribute anything, like will contribute black. But we're basically not traversing the full ray tree, but we're just going through the ray tree in depth first order. Like until we hit a light source, and only when we hit a light source the path contributes. Again, you can actually imagine that the algorithm is more efficient when there are bigger light sources, like when there are only very tiny light sources that are hard to reach, especially when they are hidden like behind some other surfaces, then they are particularly hard to reach. And those scenes will usually take much longer to converge than scenes that are lit by, say, a dome light, like a huge light source that just surrounds the whole scene. So it depends very much on the geometric settings, and there are like numerous extensions to this algorithm which help to increase the efficiency. Like, for instance, if we know that there are only small light sources, then it might be worthwhile to additionally send a bunch more rays towards the light sources, like deliberately sample the light sources and test if they are in shadow or not. Like, there are numerous optimizations to this algorithm out there, but the gist here is that we don't traverse the full ray tree, but only consider a fraction of the ray tree, and instead have the algorithm converge over time. And this is actually an example of what path tracing looks like when we render those so-called convergence frames. Like, this is the Cornell box example again. And here I'm just showing what it will look like if we let the algorithm converge over a couple of frames, and then move the mouse again and reset the convergence. And I'm actually running this algorithm on a fairly old notebook CPU, so on a current generation GPU, things would be much faster. But what you can already see here is that when I have the algorithm sit in there like for a bit, then it will eventually converge. And you can also see very nicely all that noise that the algorithm is so sensitive to. So like the most important differences of how the ray tracing algorithm and how the path tracing algorithm work is basically, like, on the one hand that we are performing those random walks, and on the other hand is the way that we traverse the actual ray tree. Like, for instance, like, consider this ray tree here where we found a number of rough surfaces, and we also found a bunch of dielectrics and a mirror material, and all those are ray surface intersections for a single ray in a ray tracer. And then there are a bunch of misses, like those triangles here indicate that we just haven't hit anything. So we are given this ray tree here, and a ray tracer, say a stochastic ray tracer or a recursive ray tracer in general, would like perform the ray tree in in some order, like for instance in pre-order or in order, depending on the implementation. And this would just look like the following. Like, we would start our traversal, like for instance in pre-order, and then we would just in pre-order traverse the whole ray tree until we actually have visited all the nodes. So, and obviously this is quite laborious, and this is just not feasible with a ray tree where we support phenomena such as rough surfaces or even diffuse surfaces. So at some point this will explode because the ray tree just explodes. And the difference with the path tracer is actually that we don't traverse the ray tree in order. So with the path tracer, when we are rendering a single convergence frame, we're not bound by the number of nodes. So we're asymptotically not limited by all the nodes in the ray tree. But what we're doing with the path tracer, we're like successively sampling individual paths through the tree. Yeah? Like this is one individual path through the tree that we've determined using random number generators and a random walk. And we're really only following this one path here, like this single slice through the ray tree. So, and asymptotically, this isn't bound by the number of nodes in the ray tree, but only by the height of the ray tree, right? By the length of this path. And this is, of course, much better. So the problem here is, of course, that we introduce a lot of noise because we're basically severely undersampling the ray tree, yeah, which is like causes other problems. But as we're using Monte Carlo sampling, we have control over the convergence rate of this sampling process. And what also helps is that we split up the computation, and that allows us to very quickly generate preview images. And the idea here is that in reality, we will not fully evaluate the whole ray tree. That is, we will never like visit all the nodes in any order that is possible, but instead we will just render until we find that noise is reduced to an acceptable amount. And this pretty much depends on the scene and on the size of the light sources and on the geometrical arrangement of the objects in the scene. But this is usually way better than naively traversing the whole ray tree. So with that, we've learned about the path tracing algorithm, and the path tracing algorithm is actually a very relevant algorithm from the family of ray tracing algorithms. Like we haven't discussed it so formally as we discussed all the other ray tracing algorithms, but nevertheless, it's a highly relevant algorithm when it comes to photorealistic imagery. Yeah, and by using path tracing and an algorithm where we traverse the ray tree in depth first order, and we just don't fully traverse the tree each time, but we rather sample the tree, we can let the ray tracing and let the light transport problems pose. But what we actually don't do, we actually don't reduce the overall work, right? Because we're just sampling the problem differently, and we're maybe a bit smarter about how we sample, and then we can maybe at some point decide that our images are sufficiently converged, and then stop convergence. But we're not actually reducing the work that we do here. And if we want to reduce the work, actually, we should. The very first thing that we should have a look at is this naive intersection test that we're doing. Like what we're currently doing is like we're given a bunch of rays, like what we formally denoted with VP, like with or we did work of O of VP. That is, we have a number of rays that is proportional to the size of the viewport, and then on the other hand we have our primitives, which we denoted as O of V. And with our test, what we currently do is we just take each and every primitive, and then we test each and every ray against those primitives. Yeah, like for instance, for this ray number 1, we will find out that the first primitive isn't hit, and we also didn't hit the second, and the third, and the fourth, and the fifth primitive, right? And then we move on to the second ray, and we find the same thing for the second ray. Like the second ray, we'll just miss all those primitives, and therefore we perform 5 intersection tests against the primitives that actually don't really contribute to our problem, right? And then we'll test the third ray, and then we finally find a ray that will hit anything. Like we'll find the 2 hits here, and then we maybe find that the hit with the blue sphere is closer than the hit with the yellow sphere. And then again, we test a bunch of spheres that we don't hit. Like for instance, this hit down here is like way out of sight of this ray, so we definitely don't hit that. And then we test all the other rays, and we find a bunch of potential hits. But most of the primitives we actually don't hit, right? Like, and then this ray here again misses the whole geometry, like misses the whole scene geometry. And this is where we should optimize, like this O of VP times V work phase here is where we should try and optimize and reduce the work that we're actually doing, because the work that we're doing is actually like much of the work that we're doing here is actually superfluous. And a very simple optimization to that is before we even start tracing our arrays, like we'll just find a bounding object around our scene geometry. And then before we actually test against the scene geometry, like when we have our array number 1, we test against the bounding box. And we found that we didn't hit the bounding box, and therefore we just cannot hit any primitives inside the bounding box. And we do the very same test with our second array, and we find out the same thing. So there we actually reduced our work. And now it is important that we find bounding objects, like the bounding box here, for instance. And it is important that the costs of intersecting the array with the bounding box isn't too high, like that it warrants testing against the bounding box first, and only then potentially later test against the primitives. There needs to be a balance, and like bounding boxes, bounding spheres, those are objects that kind of make sense. Like we could maybe try to find objects that have a tighter fit around our scene geometry. And the question is really, if there is a tighter fit of our object around the scene geometry, does that warrant the extra cost for testing against the bounding object? So this is what we have to optimize for. And in our case with the bounding box, I mean, the third ray will actually hit the bounding box, right? And then in our case, we really test the primitives. Like we then find 2 hits, and 3 of the primitives won't be hit, and then we perform actual work, right? Like, and so far we have performed 3 tests against the bounding box and 5 tests against any objects. That is, we tested 8 objects so far. Like we intersected the array with 8 different objects so far, and this is opposed to 15 tests that we would have performed if we didn't have the bounding box, right? And I mean, you can see where this is going, right? You do this for the 4th ray and find a bunch of intersections. You do this for the 5th ray, and you intersect this sphere here. And then for the 6th ray, you again can just cull the whole array and don't have to perform any work. So this principle will help us to greatly reduce the work that we're actually doing. So, and the next inefficiency here is that whenever we hit the bounding box, then we actually test against a bunch of rays, like this ray number 4 here, or this ray number 3 really, is highly unlikely to ever hit this dark blue sphere down here, right? And therefore what people do is they take the original geometry, and then they build hierarchies over those bounds. Yeah, like you started with a bunch of objects that you group together, and then you compute bounds for the groups, and then you take the group bounds, and over those group bounds you again compute bounding boxes, and that allows you to build hierarchies. And what I just constructed here in 2D is what one would call a bounding volume hierarchy, or a BVH. And you might actually have heard this term. I don't know, but nowadays it's a very popular term because NVIDIA ray tracing hardware uses bounding volume hierarchies. And they actually advertise that, like when you dig a bit deeper into the technical papers that NVIDIA publishes on their RTX, RT-Core hardware ray tracing extensions, then you will read about BVHs. And this is just what I just showed you is just a BVH. And there has gone so much research into BVHs in the most recent years, and thus we're going to talk about this principle. Like, we're going to talk about BVHs. We're also going to talk about alternatives, and we're going to talk about the different pros and cons of the various data structures, and also of the various construction and traversal schemes for those data structures. And this is what we'll talk about in the following.
Yeah, and I mean, the problem is really that we, in order to achieve high realism, have to trace many more arrays, and at the same time, with increasing scene complexity, generally testing arrays against all the scene geometry is just not feasible, and therefore it is just our only option to use some type of acceleration data structure to accelerate this process of finding closest or finding any hits in the scene geometry. And the idea is really that we find some type of bounding object to group our primitives, then test against the bounding object, and only if we hit that bounding object, then we only consider intersecting the primitives that are contained inside. And that allows us to build hierarchies of bounding objects, and that reduces the complexity of the query, like the query to find the closest hit, which originally was an O of n query in the number of primitives tested. And using bounding objects and hierarchies of bounding objects allows us to reduce that to logarithmic complexity in the number of primitives. Yeah, for the discussion, let us just consider this very simple scene here that is comprised of 4 spheres, like the orange and green sphere and the blue and red sphere here. And what we're after is a acceleration data structure, and we want to construct a hierarchical acceleration data structure. And like before, we already discussed BVHs, and a possible BVH for this scene here could look like the following. We just group together those 2 pairs of spheres, like the orange and the green sphere and the red and the blue sphere. We just group them together and compute their common bounding boxes, and that would give us 2 leaf nodes to our BVH. And then what I'm not showing here is we would construct a root node to the BVH, and the 2 leaf nodes would just be the child nodes of the root node. And this would be one possible acceleration data structure and one possible configuration. Like there's actually a multitude of potential configurations even for BVHs that we could have. Like we could have found different groupings for the leaf node. Like this is just one that we might have found out heuristically, using some heuristic that tells us that it's a good idea to group the primitives in that very way. So, and from this simple configuration, there's a bunch of observations that we can make, and that actually define like the key pros and cons of the bounding volume hierarchy data structure. So on the one hand, what we can see is that when we do this type of object partitioning, and this is what we're doing with bounding volume hierarchies, there is an upper bound on the number of nodes that the hierarchy can have. Consider we would just assign 1 leaf node per primitive, and that would give us the maximum number of leaf nodes as just being the number of primitives, right? And say we're constraining ourselves to just using binary BVHs, and therefore we could also tell the number of inner nodes, right? Because the number of inner nodes would just be the number of leaf nodes minus 1. And therefore we could just exactly tell in advance the number of nodes that the BVH is comprised of. That would just be 2 times the number of primitives minus 1. This is actually very powerful. This would allow us to pre-allocate the whole BVH in advance. And this is very helpful. Like when we usually when we have moving objects and dynamic scenes, then construction performance is pretty important. Like we want to optimize for the time it takes to actually build those BVHs. And dynamic memory allocation is actually quite costly. And if we don't have to perform any dynamic memory allocation during constructions, but if we can just a priori allocate the whole data structure once and for all, that's actually very helpful in regards to performance. So that's actually a very important pro of the bounding volume hierarchies. There's actually a con that we can see here, and that is overlap. The most important quality criterion of BVHs is overlap, and we can see that those 2 nodes here overlap in space, right? Here, this region of space is where there is overlap. And overlap can actually lead to very severe traversal overhead, because this usually means that we're traversing BVH leaf nodes and intersecting rays with BVH leaf nodes, although we're not really hitting any primitives inside of them. So the most important quality criterion actually of BVHs is how much overlap they have across their nodes. So while BVHs are one way to partition objects, an alternative to partitioning objects is to actually partition space. Like this here is a typical space partitioning. It's what people would call a KD tree. like in this case, a 2D tree, a two-dimensional tree. And what's the significance of a KD tree is, on the one hand, that it's a spatial partitioning data structure, and we have so-called hyperplanes, so split planes in the dimension that the tree is embedded in, that partition space into half spaces. So that makes KD trees so-called binary space partitioning trees. And what makes them KD trees is actually the fact that the split planes, the hyperplanes, are axis aligned. And you can already see here that those split planes, like when we place those split planes, we usually use some kind of heuristic. And that heuristic is usually guided by the objects. I mean, we want to somehow group and organize the objects, but it doesn't actually partition the objects, but it partitions the space around the objects. So, and we can actually see that this leads to replication. Like, for instance, this blue sphere here falls into both half spaces, like in the upper and in the lower half space. And so we need to store a reference to the blue sphere in both half spaces, which is actually one of the downsides of KD trees and of object partitioning in general. Another downside is that we, unlike with the BVHs, don't know the memory consumption a priori, so we cannot just a priori allocate arrays that will hold the KD tree or the acceleration data structure. And therefore, like in general, and there are also other reasons why this is the case, but in general, construction of this type of data structure usually takes a bit longer. Like in the very early days of real-time ray tracing, like in like around 2002, 2003, and that time, people hadn't agreed upon the best acceleration data structure yet. While like nowadays, people most of the time actually use BVHs. But back in those days, when the first real-time ray tracers came out, people actually used KD trees because scenes that were dynamic actually were pretty much out of reach for real-time ray tracers anyway. So people were actually happy when they could perform ray tracing with static scenes in the first place. So KD trees were actually quite popular. And what was agreed upon is that KD trees were a bit faster to traverse actually. And that, on the one hand, has to do with overhead, and on the other hand, also has to do with how your array can hop between the different half spaces. Like, there are actually pretty efficient traversal schemes out there that you can use to traverse those half spaces. So in general, those object partitioning data structures tend to be a bit faster to traverse, but on the other hand, usually are much slower to construct. And as a matter of fact, like, people nowadays usually use BVHs, and there's been so much research into both BVH traversal as well as BVH construction that it is there's actually pretty much a wash between the two data structures, and it's the differences in traversal speed are actually pretty little, and in general, people agree upon that the advantages from using object partitioning pretty much outweigh the advantages that you might have from a potential spatial partitioning. Yeah, like with the two data structures that I just showed you, the partitionings usually used partitioning primitives like bounding boxes or hyperplanes that were axis aligned, and this is actually pretty common to do. Like, for this very scene here, for instance, we could imagine a more efficient partitioning actually if we allowed for non-axis aligned planes. And in fact, those partitionings are quite often faster to traverse, but the real problem with them is that they are much harder to construct actually. Like, the construction time for a hierarchy like this, for a fairly complex scene, depending on the heuristic that you use, but it's usually on the order of n to the 3 in the number of primitives. So, and the relatively high construction times are the primary reason why people nowadays usually use axis-aligned data structures. Yeah, the question is really if we want to use object or space partitioning, and it should also be noted that this decision also pretty much depends on the characteristics of the scene. Like, for instance, if we even have dynamic geometry, or if the geometry is also always known to be static, And then what's also important is like the distribution of the scene geometry. Like for instance, if we really just know that the scene geometry is kind of uniformly distributed, like not like this like the geometry here, but if we knew that we have like primitives that are all of mostly the same size, and that in most of the regions in space we have about the same occupancy of primitives, then it can actually be very useful to use uniform grids as an acceleration data structure. Like uniform grids have this huge advantage that on the one hand they have really a minimum of additional memory that they require, and that is mostly because the grid can be fully defined by the constant cell size and by the size of the grid. And the storage overhead for that is really just goes to zero, like really just a few integers and floating point numbers that we have to store. In contrast to a BVH, like a BVH can is very likely to use about the same space that we need to reserve for the actual primitives. So on the memory side, uniform grids are very superior. And like when we have data that is distributed so that we can make use of uniform grids, that's actually very good, because they're actually, in that case, they're actually pretty fast to traverse. Like when we want to test a ray against a uniform grid, like we don't have to even perform real intersection tests. Like we would just basically project the uniform grid, like we would basically rasterize the rays into the 3D uniform grid, and that would tell us which cells we would overlap. And like in that case, where the data is very evenly distributed, uniform grids make perfect sense. But unfortunately, the data is not always uniformly distributed, but quite often we have primitives that differ in size, that differ in spatial distribution, like the spatial arrangement might vary quite a lot. And what people usually refer to this problem as the so-called teapot in a stadium problem. Right? Like this should basically indicate that we have like a huge geometry, and then we have a very tiny but very complex object that is like somewhere in the middle of that scene. Yeah, and I mean, with the teapot in a stadium problem, we could just like, if we knew we had a teapot in a stadium, that we could just handle this specially. But the problem is that you never really know about the spatial arrangement of the objects or of the actual sizes, and that makes uniform grids actually quite inflexible. And this is the reason why they are not so popular, and why people usually use hierarchical data structures and prefer them over uniform grids. Yeah, and the various types of hierarchical data structures we actually already learned about, like the BSP trees, which just subdivide space into half spaces and use hyperplanes for that, and the KD trees, which are a special kind of BSPs, in that their hyper split planes are axis aligned. And we also already talked a lot about bounding volume hierarchies. And here on the left side, you can actually see that bounding volume hierarchies are not necessarily comprised of axis-aligned bounding boxes, like of AABBs, but they can actually be comprised of all sorts of bounding objects. Like the question is really 3 pairs of parallel planes. Like this test is very efficient, and on the other hand, in order to test a ray against a sphere, we have to solve a quadratic equation, and for that we have to deal with square roots, and with a square root, the square root is actually an operation that, on the one hand, is an iterative operation where you use like Newton refinement and things like that, and on the other hand, it's a operation that uses quite a lot of floating point instructions, and therefore has quite some potential for round-off errors. So as there is potential for round-off errors, we have to incorporate that into the data structure. So because we can make a rounding error, we have to make a more conservative estimate about the actual bounds, and that is why people would usually introduce a bit of slack so that we are guaranteed to actually hit the primitives, and that round of errors wouldn't result in false negatives, right? So, and those considerations are also what determine what a good and what a bad bounding object is. And without any judgment, well, what I can say is that by far the most popular bounding object nowadays is the access line bounding box, the AABB. And this is actually when we later have a look into hardware ray tracing. This is actually the bounding primitive that the hardware actually uses, and as a matter of fact, also all relevant ray tracing APIs and libraries that are out there also use access aligned bounding boxes, and in fact they use BVHs of access aligned bounding boxes. So to sum that discussion about KD trees versus BVHs, to sum it up, is like what we're talking about is traversal efficiency versus construction efficiency. So in regards to traversal efficiency, it's just that ABBs may overlap while half spaces per definition don't. And the amount of overlap is just a quality criterion for a BVH. And on the other hand, like we always want to have a balance between traversal efficiency and construction efficiency. As usually there's just a trade-off. Like usually when we have a data structure that is fast to construct, we usually have to pay that at the cost of slower traversal, and vice versa. Like a BVH that is really optimized for traversal is usually a bit slower to construct. So we have to make this trade-off between traversal and construction performance. When it comes to BVHs, and this we already discussed this, is that the memory requirements are known a priori. So because we just know what the number of leaf nodes will be, we have an upper bound for that, and then we also have an upper bound for the number of primitives. And what's also nice about BVHs is that they allow for partial rebuilds. That is, we can take the BVH, like we can take subtrees of the BVH, and we can like arbitrarily move those subtrees around and build a new BVH over just the subtrees. And regardless of what the quality of the tree will be, well, we might introduce some significant overlap, for instance. The BVH that results from that will still be correct. So that's important. And there's actually quite some potential to make use of that. Like refitting is like on the order of can be one or even two orders of magnitude faster than actually rebuilding the BVH from scratch. And this is actually very helpful when we deal with dynamic scenes. So there's gone a lot of research into improving the construction times for a BVH without impacting the traversal speed too much, and we will discuss a little bit what that implies on one of the next slides. And so, in certain cases, we might actually run into several problems with BVHs, and that actually has to do with when we have a combination of very large and very small geometry. And this is where BVHs are actually quite ineffective. Like when we have a huge geometry, like a bunch of huge triangles, and then there are also like a number of very small triangles in that scene, BVHs tend to be quite ineffective. And therefore, there also exist hybrid approaches that in certain situations allow us to introduce so-called spatial splits. Like there are basically hybrid approaches between KD trees and bounding volume hierarchies. I guess this is actually a bit of an advanced topic. Like in this case, we, for instance, will lose certain properties like the a priori known memory requirements. But suffice it to say that there are hybrid approaches out there, and they're actually quite popular. Like the SBVH approach is actually quite popular. Another approach that is actually quite popular is so-called two-level BVHs, and this also has to do with what is called instancing. Like the idea is basically that you have on a mesh level, like on the bottom level, you have a very highly detailed geometry, and that geometry might actually be replicated. Like you have like a single base mesh, and that base mesh is replicated several times, but this is not a necessity, so this is not a requirement. And then, like, you have several of those relatively complex bottom-level BVHs, and then on top of that, you have a top-level BVH, a so-called top-level BVH. And the top-level BVH can be rebuilt relatively fast. And that allows for certain, like for rigid motion, or for instance, like if you have like consider like a 3D model of a freeway, and there are cars driving around, and each of the cars has its own BVH, and the car itself will never change, but the cars themselves move. So we would model the freeway. We would model the freeway with a top-level BVH, and each of the cars would have its own bottom-level BVH, and the bottom-level BVHs would never change, but the top-level BVH would change all the time. That is when the cars drive. And then just consider that we have two cars that are exactly the same make, like they are indistinguishable, and then we would use instancing for that. That is, we would just store the car once in memory, and then we would replicate it by basically associating two transformation matrices with the base mesh. Like we would have one base mesh, and when we replicate it, we would store with the copy of it, we would store a 4x4 transformation matrix or a 4x3 transformation matrix that would tell us the orientation and position of the object. And we would not actually store a copy, but we would actually store a reference to it. And this concept would be called, it would be a so-called two-level BVH. So we have a top-level acceleration data structure, or BVH, and a couple of bottom-level acceleration data structures. And as a matter of fact, this is also a mode that is supported by NVIDIA's RT Core hardware that we will also discuss during this lecture. Yeah, and as BVHs, and in particular BVHs of AABBs, are so popular, we will in the following concentrate on them. And like, there's actually a fundamental problem with AABB BVHs, and this is the problem that I'm depicting here on this slide. And the fundamental problem is really that when we have an array that grazes the geometry, yeah, like that is like kind of tangential to the geometry. So it will never actually hit the actual geometry, but it will graze the geometry, and therefore we will just hit each and every bounding box that the potentially curvy geometry is organized with. And this is actually a very huge problem, so that there are certain arrays that, depending on how they actually interact with the geometry, can result in highly expensive intersection tests. Like you can see this kind of nicely here on this slide. Like here's this teapot mesh, which is a bit curvy, right? Because the teapot itself is like a bit rounded, and then you can see that where the teapot is rounded, the BVH that I constructed from that is actually quite complex. So you can actually see that when we like this here is a depiction of the costs of the BVH traversal. Like blue and green are relatively cheap, and yellow, orange, and red are relatively expensive. And you can see that here, where the geometry is relatively complex and where arrays potentially graze, that there the costs are highest. And this is actually a real problem with bounding with AABB bounding volume hierarchies. Like that, there are those AABB corners that grazing rays will run through even when they don't hit the geometry. This is a fundamental problem with AABB BVHs, but nevertheless, all the other alternatives, like alternatives where we use so-called OBBs, that is oriented bounding boxes, etc., have other issues. Like mostly it's about construction and finding good BVHs from them, so that still AABB BVHs are what is currently used by the state of the art. And if we want to construct a AABB BVH, like an axis-aligned BVH, there are several options that we can use, and the most popular options are to either construct those BVHs top-down, or to construct them bottom up. So what needs to be said is that however we construct a bounding volume hierarchy, we will always employ a heuristic. Like it can be shown that constructing an optimal BVH is NP hard, and therefore we have to employ some sorts of heuristics. And a very common heuristic is the top-down construction of the BVHs. And the top-down construction method will just greedily split bounding objects into two bounding objects, or will decide that we make a leaf and thus stop the recursion that we're currently in. So top-down construction is usually done recursively. And a top-down BVH construction is actually a build routine that is very commonly used on CPUs for reasons that we will discuss in a little bit. Like in the basic outline of the function to top-down construct a BVH is as follows. Like we have our function build hierarchy that is called recursively, and we will start just by calling it for the root node. So we will just make a root node, which is a bounding box, an AABB, that just includes all the objects in the scene, right? So this is a bit different from the examples that I showed before, where we started with the leaf nodes. We now instead start with the root, and we will now gradually split the root node into several inner and leaf nodes, depending on certain heuristics that we will use for that. So when we build our hierarchy, we're presented with a node, and in the beginning this is the root node, and we will later recurse into that function, and then we have to make a decision if we want to split the node or if we don't want to split. And we will talk about what that implies, like what we do in order to decide if we want to split or if we don't want to split. If we don't want to split, we just make a leaf, right? So we just take all the primitives in the node and we make a leaf and we're done. And if we decide that we do split, the split function will tell us, given the current node and the primitives that are in the node, will tell us what the AABB to the left and what the AABB to the right will be. Yeah? So left and right is a bit like we're usually having to make a decision along which axis we split. And here we also usually use a heuristic, and quite often what we just do is we use the longest side of the AABB and just split along that side. So this is the first heuristic that we use, where we have to make a decision along which axis to split. And then along that axis we have a left and a right, or an upper and lower, or a front and back bounding box, but here I'm just commonly refer to them as left and right. And the split function will tell us the two bounding boxes. And then the next thing that we need to do is we need to partition all the primitives of the original node, like of the parent node, into the left and into the right AABB. And then we call this build hierarchy function again, and we call it recursively with the left and with the right node that we just constructed. So this is the basic routine that we use in order to construct, to top-down construct bounding volume hierarchies, binary bounding volume hierarchies of AABBs. Like here it's important to say that it is not a necessity that we construct binary bounding volume hierarchies. Like they are popular, but for instance, NVIDIA hardware is, NVIDIA doesn't publish this, but it's quite likely that they don't use binary BVHs, but that they use BVHs with a wider branching factor. And the same is also true, like for instance, for Intel's very popular Embry library, which is a ray tracing library that is very widely used and that is optimized for Intel CPUs. And there, as the library is open source, it is known that the BVHs in Embry use a wider branching factor. So nevertheless, for simplicity, we will concentrate on binary BVH construction. And the question now is how to determine if we split or not. And there are actually like a bunch of different heuristics out there that can be used, and those actually determine the quality of the resulting BVH. Like there are very simple heuristics, like we can just take the AABB of the node that we're currently splitting and splitting it in the middle, right? Like just take the size of the AABB and compute where the midpoint is, and just place the split point, the split plane there, and be done. Like this would be called a middle split. And what we could also do is like we could just count how many primitives are there, and then find the primitives median, so that we have like an equal number of primitives to both sides, and then split and then sort those primitives into the left and into the right node, and split just there, so that we have an equal number of primitives per left and per right node. So those two are very simple heuristics that can be used, but nowadays what people use in order to construct high quality trees is the so-called surface area heuristic. And the surface area heuristic is basically a cost function that we use to decide if we split or not. So, and this cost function works as follows. It's a cost function that penalizes the area of both the primitives and the area of a potential AABB that would be associated with a node if we create a node. Like we have to make a decision if we either test our array against the primitives, or if we test it against an additional node. And the surface area heuristic just considers the surface area of either all the primitives or of the AABB that would be associated with the node that we would create. As input to the surface area heuristic, we use the n triangles that are already in the current subtree, and we consider the like their extent. Like what I denote here as the volume V, which is actually like the extent which is basically the bounding volume. And then we determine the costs that would be associated with a potential split into two nodes L and R. And a potential split that we would consider would see us distributing NL primitives to the left and NR primitives or triangles to the right. And the extent, like the region of space associated with that, like the volume and space, would be VL and VR. And our cost function is now basically comprised of the surface area of this extent to the left over the total surface area of the subtree times the number of triangles that go left, and then plus the very same thing for the right node that we would construct. And then we have two like constants that we can use as basically as user weights, like as user parameters that we can use to either like on the one hand we have costs that would be associated with performing a ray triangle intersection. Like we would try to assess what the costs would be if we performed a ray triangle intersection. And we would also try to assess what the costs would be that would be associated with traversing the hierarchy, like with performing extra traversal through the hierarchy. And based on this cost function, we will compute this cost function. And the cost function would tell us the cost of the current split that we're considering. So, and equipped with this cost function, we can, given a certain plane, make an assessment how good that split would be. Like, and if we want to compute that split. And what one would now do is we would like first of all we would initialize our costs with something like infinity or something. And then we would like determine a bunch of split plane candidates. Like we will discuss later how we do this, but we would determine a bunch of split plane candidates. Like there are several heuristics out there that we can use to determine split plane candidates. But for now, we just assume they are given. And then we would determine their SAH costs for all those split candidates. And then we would choose the plane with the lowest costs and determine AABBs for that. And we would also determine how many primitives would go in there. So, and then in order to determine if we should really split or if we should make a leave, we would just compare those costs against some constant that we would define a priori, and that would tell us if our costs warrant a split or if we should make a leave. So with that, I'm closing for today. In the next session, we will learn a bit more about the surface area heuristic and about BVH construction.
We'll learn about how to determine split candidates. We will also learn about other construction schemes, like, for instance, bottom-up BVH tree construction. And then we will finish our discussion on ray tracing. We will have a bit of a discussion on real-time ray tracing and what people do in order to achieve real-time performance with their ray tracers. And after that, we will finish our discussion on ray tracing, and then we will have an intermezzo about parallel rendering. And this intermezzo will actually close our discussion of rendering algorithms and computer graphics. And I hope that you tune in next time when we discuss all those topics.